Okay, well, happy Friday, end of week 8. We're only 2 weeks left, and I feel like the last 2 weeks always go by quickly. Um, anyway, so we did numeric methods, we did root finding, numeric optimization, and then we're gonna move right along, and we will start doing, I guess, computer-based statistical inference. So this will be things like randomization tests and bootstrap, things like that. So we'll do some testing there, and so we'll start covering that next week. Now, a lot of that involves creating hypothesis tests and thinking about that, and so. I want to do a little bit of review of statistical inference. And so many of you, it's going to feel boring because you've seen all of this stuff before. But some of you took Stats 10 here at UCLA. Some took AP Stats in high school. Some might have taken Intro Stats at a community college. I don't know, is there some other, I don't know where everybody got their Intro Stats exposure. Okay, and I started doing this because the last homework 6, which will be released I guess next week, covers a lot of kind of statistical inference stuff. And then when I looked at some of the responses, especially like what does the p-value mean in this context, I felt like some of the answers are like way wrong, and so I want to review this and make sure everybody has a correct understanding of statistical inference and how a lot of this stuff works. So I'm going to try to compress all of, I don't know, Stats 10, all of Intro Stats into the next 45 minutes or so. Okay, so some parts will work well and some parts maybe I'll just have to kind of compress in there. So we'll do a quick review of Intro Stats. And this almost feels silly to talk about this, but I also feel like maybe this isn't really emphasized. So, everybody knows what the mean is. Everybody knows what the median is. But I don't know if we have a real good, fundamental or conceptual understanding of why the mean and the median or whatever what they are. And so these are ways we talk about where's the middle of your data. Okay, and the two key differences is that the median balances so both of these can be thoughts of places that balance our data. The median balances the number of points that are lower or higher. So on the values below the median, you have the same number of values below the median as you do values above the median. The mean also is a balancing point, but it balances the deviations below and the deviations above. Okay? And so because the mean balances the deviations, if you have a point that is particularly deviant, okay, really high above, skewed to the right, because the mean is trying to balance the deviations, the mean gets quote unquote pulled in the direction of the skew. All right, and because of that, for skewed distributions, we often prefer to use the median. But just to kind of illustrate this, here is just a very silly small sample of data: 1, 2, 3, 4, 10, and 10. And what is, there's no right or wrong answer for which is the better measure of center. Okay, the median, the center is 3.5 because I have 3 points below the median and 3 points above the median. Okay, 1, 2, 3 are less than 3.5, 4, 10, and 10 are above the median, 3 points below, 3 points above. The median balances the number of points. Okay, whereas what is the mean? The mean balances the deviations. So here, if you select 5, then the deviations 4 is -1, 3 is -2, you have -3 and -4. So the deviations below add up to -10. And then you have the 2 points at 10. So from 5 to 10, your deviations are +5 and +5, and the deviations above are +10. So you get -10 balances out with +10, and the mean balances the deviations. And so you could see if I had changed this last number from 10 to, say, 100, now I have this really huge deviation far above, and so I have to kind of, this red line would have to slide, way out to the right. Okay, so so the mean is affected by those kinds of outliers. Okay, so we can use the mean or the median to balance what we have there. Okay. Then you also have to describe spread. Are your values spread out, or are they all very similar to each other? And we use the variance and the standard deviation. Okay. So smaller variance, smaller standard deviation means your data values are all very close together. So imagine looking at the ages of students in an elementary school classroom. So if you go to an elementary school and you go to a second grade classroom and you say, how old is everybody? Everyone's going to probably say, I'm 7 or 8, right? At the beginning of the school year, I think everybody's at 7, and then as the school year goes by, some of the kids turn 8 and things like that. But pretty much everybody's going to be 7 or 8 in a second grade classroom. Okay. Versus if you go to another room, say you go visit like the DMV or a doctor's office or something like that, and you say, how old is everybody here? Now you're going to have a wide range of ages, right? You're going to have teenagers, you'll have young adults, you'll have middle-aged adults, seniors, children, things like that. You're going to have a kind of ages that are all over the place, so you have much greater variance in standard deviation. Everybody has kind of different values. And the definition of variance that I like to think, or like to use, is we say the variance is the average squared deviation from the mean. So if you go back to this slide, I have these yellow or orange lines represent deviations from the mean. How far is a point from the mean? And then we square all of those deviations and we take the average of that. Okay, and that's our variance. And so if all of the points are very close to the mean, then the deviations are small. Your average squared deviation is very small. If all of the points are far away from the mean, meaning they're very spread out, then your average deviation is going to be huge. Okay, and then the standard deviation is just the square root of the variance. So we have that. Okay, so if you think about what is the variance, the formula for the variance is we say, all right, we take our each individual point xi, subtract off the mean. That's our distance from the mean, and then we square that distance from the mean. Okay, and then if I add them up and divide by n, we would get the average squared distance from the mean. But the problem is that's going to be biased. And then if I do, but if I add them up and divide by n minus 1, that gives our variance formula. Why is this one biased? If you just add them up and divide by n, why is that variance there biased? You guys proved this in 100B, right? Huh? Do you guys have an intuitive answer for why we have to divide by n minus 1? Because you say, oh yeah, if you divide by n, it's biased. So you want to divide by n minus 1. So dividing by n is biased in that your estimate of the variance is going to be too small overall. Because what we're trying to do is we're trying to estimate the population variance, which is how far, what's the average squared distance from the population mean mu. And so if this formula would be correct if we replaced x bar with mu. If we knew what the population mean is, and we plug that in, if we knew that the population mean is, say, 10, and I plug that in, then this formula would be correct if I knew what the population mean is. And so actually some stats textbooks will say if you're dealing with the population, you just do x minus mu or whatever, and you divide. So if we had the population mean mu, we could plug that in, and this would be the correct formula. But our issue is that we don't have the population mean, and we are estimating the population mean using x bar. So we're taking the mean of our sample, and we're going to use that as like the estimate of the population, and we're going to calculate our distances from the mean using our sample mean. And so because x bar is coming from the x values in our sample, that value x bar is going to be right in the center of our sample, okay? And so the distances from x bar will always be a little bit of an underestimate of what the distances are from the true population mean, okay? And it turns out the exact value that we need to correct it by is n minus 1, okay? But anyway, that's that. So the other, I guess, thing that we have to introduce is the normal distribution, and you guys are all very familiar with that. Unimodal, symmetric, continuous, looks like this, okay? And the key values here, we have these numbers memorized. Yes or no? Maybe 68, 95, 99.7 for 1, 2, and 3. Okay, you should. So if you're going to call yourself, there's a few things you need to have memorized if you're going to graduate with a degree in stats and data science or data theory or something. And this is one of those things, 68, 95, 99.7. And then the other, I would say, is the PDF of the normal standard, at least the normal PDF of the normal distribution, or PDF of the standard normal distribution, right? Square root, 1 over root 2 pi, 2 sigma pi, okay? So anyway, 68% are within 1 standard deviation, 95% are within 2 standard deviations, and then almost all of it, 99.7, only 3 out of 1,000 are greater, beyond 3 standard deviations from the mean, okay? And that's going to be important going forward, because a lot of things end up looking like the normal distribution. When we do research and statistical inference, we have some kind of research question, and the thing we wish we could get is the population. The population is everybody who's relevant to answering this question. So you might have this question like, what is this drug effective at treating some disease? And the population would be everybody who has that disease. But the problem is that the populations are always too big for us to study directly. There's just too many people. You can't study every single one. Or the other problem is that maybe you can't even track down every single person in that population. There's just no way to get them. So, especially if we're talking about some kind of medical condition, like who has a particular disease, there's, a lot of people don't even know if they have the disease or not, okay? That was a big problem with COVID, was that a lot of people were asymptomatic. They carried the virus, but then didn't show any symptoms, and so it would spread. And so who has a particular disease? I mean, this is a problem for anything, right? Just people maybe have cancer or something, and they don't even know it until they show symptoms, and then it's too late. So the population would be everybody who has some disease. And the problem is that we can't either track down every person with the disease, or there's just, we don't even know who's in that population. There's too many people in that population. Let me give you your first view quiz answer, which is going to be the letter E. E as in elephant is our first view quiz answer. So we say, well, we can't get people from the population directly. So what we will work with is a sample. And so this picture is supposed to be the idea of selecting individuals from the population to be part of our sample, okay? And so we will study the sample, and based on the sample, we're going to draw conclusions about the population. And so what we're hoping for is our sample is representative of the population. We want the people that we select to study to be like a miniature version of the population, okay? And one method that should produce representative samples is random sampling. But random sampling, it's, one thing, it's not guaranteed to produce a representative sample. It's random after all. So by random chance, maybe you get too many from one group and not enough from another group, okay? And so if your sample is not representative, it is said to be biased. The term biased in statistics just, it doesn't mean what the normal day-to-day language of biased is. Our day-to-day language biased sounds very kind of like a bad thing, like it's malicious, like you're out to try to oppress a group of people or something like that. In statistics, just biased, it means it's not the actual thing, right? So if your estimator is biased, it's not going to converge to the true thing. And if your sample is biased, it just means it's not truly representative of the population, okay? It's not that there's malicious intent behind it, okay? And so when we do take a random sample, we will take like the mean of your random sample or standard deviation of your random sample. You calculate some kind of statistic there. But because that sampling process is random, if somebody else were to take a different random sample, they would get a slightly different sample mean, right? So if I take a sample of 100 people and you take a sample of 100 people, and I calculate the mean of my sample and you calculate the mean of your sample, we're probably not going to get the exact same values. We're going to get a different group of 100 people, and we're going to get different values. But if we did this a whole bunch of times, we're going to find that some of these values, certain ranges of values, are more likely, other ranges are less likely. And so if we kind of plot and chart all of the different possible sample means that we get, we would get the sampling distribution of the mean. And you can get a sampling distribution for any sample statistic. So if you calculate, what is the standard deviation for this sample and what's the standard deviation of your sample, you would get a sampling distribution of the standard deviation. So however you want to do it. So we can I'll simulate a sampling distribution here. And so I'm going to just start off with some hypothetical population. I'm going to say just arbitrarily, I'll say the population is normal, the population has mean 0, and the population has standard deviation 1. So I'm going to just start off with the standard normal distribution. I'm going to say that's my population. And what I want to do is I want to just see what kind of random samples I get. So I think I'm going to draw random samples of size 16. And we're going to say, all right, if I draw 16 random values, what kind of values do I get? And I'm going to calculate the mean of those 16 values. And then I do this again. I'm going to draw a different set of 16 random values. And I say, what is the mean of those 16 random values? And I'm going to do this over and over and over and over again. I'm going to keep track of the sample mean from every single one of these random samples. And then at the very end, I'm going to look at the distribution. What are all of the different sample means I got? And what we'll find is the sampling distribution is going to follow a normal distribution. So that's the central limit theorem. If you have a big enough sample, then the sampling distribution of the mean will follow a normal distribution. And that normal distribution will have a standard deviation or standard error of sigma divided by the square root of n. So the bigger your sample, the smaller your standard error. The sample size is large enough is just a loose loose definition. If the population is normal, any sample size is large enough, you can take samples of size 1, really, and that those samples will be normally distributed, and obviously bigger samples will be normal. But if the population is not normal, you need a bigger sample size. Our rule of thumb is, most things in nature and stuff, a sample size of 25 is big enough for most cases. But if it's like really skewed, then 25 is not going to be big enough. You need something bigger, or you need to do some kind of transformation on your data. But anyway, that's but in most, central limit theorem does say if n is big enough, it will follow a normal distribution no matter what the population is. But that n might need to be like really big. So anyway, these are just some demo examples. So this is my standard normal distribution. I drew 16 random values from the standard normal distribution, and I've sorted them from least to greatest. And I have the individual values that I've drawn shown on the bottom. This is what we call a rug plot, because it looks like little, I guess, hairs of carpet on the ground or something. So my 16 values were what? Negative 2.21, negative 0.84, and negative 0.82. Those are so close to each other that they kind of merge into one line here. And then I also have negative 0.63 and negative 0.62, and again, those are kind of so close that they've merged together into one line. And then I've got negative 0.31, negative 0.04, 0.18, 0.33, 0.39, 0.49, 0.58, so on and so forth. All of these little ticks. So there should be 16 little ticks here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Yeah, 16 values. And if you take the mean of these 16 values, you get 0.092. And that's what this red line right here represents. So that's the mean of those 16 values. I repeat this again, so you'll notice the rug plot changes to 16 different other values. So these are just another set of 16 values. And I calculate the mean of those 16 values, and I get 0.096. Just an ever so slightly different mean. So different rug plot. Here's another set of 16 randomly selected values. Okay, and with this set, I guess the mean is negative 0.197. Here's another 16 random values, and the mean of these values is 0.426. Here's another random set of 16, and the mean is negative 0.176. Okay, and so just kind of, this is just different random values there, just to kind of show the different values, and so you can see the actual values drawn there. And so here is just some code to repeat that process 10,000 times. So so I just wrote a for loop, and I said, basically for I in 1 through 10,000, what you're going to do is you're going to select 16 values at random from the normal distribution. So we use our norm to generate 16 random values from the normal distribution. I'm going to put that in my random sample. I calculate the mean of my random sample, and I'm going to store that into sample mean square bracket I. So I'll do this for values 1 through 10,000. Okay. Yeah, this code could have been written more efficiently with just one line if I use something like replicate, but I think the for loop makes it very easy and clear what's happening. Okay, so anyway, after doing this 10,000 random samples of 16, if I say, hey, what is the mean of all of my sample means, the mean of means there, I get something very close to 0. I get 0.0015, so not exactly 0, but pretty close to it. What's the standard deviation? This is basically the standard error there. I get something very close to 0.25, 0.25018. Okay, theoretically it should be 0, and theoretically it should be 0.25. And we do get something very close to that. But again, this is just based off of 10,000 and not infinity. Infinity would drive us to 0 and 0.25, but 10,000 doesn't quite get us there. Here is a plot of all of the different sample means. And we can see most of our values are near 0. My standard error, again, is 0.25. So 0.5 to negative 0.5 represents two standard errors, so about 95% are between 0.5 and negative 0.5. If I go to 0.75, that's going to get us almost everything, 99.7. And we can see, yeah, you know what? Is it possible to get a random sample of 16 values where the mean of all 16 values is like 1.0? And it is possible, and it looks like that happened, what, once or twice? Okay, so out of 10,000 random samples of 16, I did get a random sample where the mean was 1.0 or higher, but it happened very, very, very rarely. So maybe once or twice out of 10,000 things. So not impossible, but very rarely. Okay. If you say, hey, is it normal? You create a normal QQ plot. Yeah, you get something that looks pretty much like a straight line. So very, very simple. Very much like the normal distribution there. Okay, so so we take this fact, okay? The central limit theorem says when you take a random sample and you take the mean of your random sample, that mean, the sample mean, whatever it is going to be one of these, 10,000 values here, and which means it's going to come from a normal distribution. That's what the central limit theorem says. You take a sample, random sample, you calculate the mean of your random sample. That sample mean of that random sample comes from a normal distribution, which means most of the time it's close to the population mean, and only very rarely will it be more than 2 standard errors away from the population mean. So what did I write here? Central limit theorem establishes that the mean of a random sample comes from the normal distribution centered at mu with standard deviation or standard error sigma over the square root of n. That standard error shrinks as the sample size increases. Empirical rule says that 95% of the time a random value drawn from the normal distribution will be within 2 standard deviations of the mean, and therefore when I draw a random sample, there's a 95% probability that the mean of the random sample will be within 2 standard deviations of the population mean. So whenever you're going to draw a random sample, 95% probability that this random sample will produce a sample mean that's within 2 standard deviations or 2 standard errors of the population mean. And so we take that reasoning and that logic there, and we flip it around. And so now if I have a random sample and my random sample has mean x bar, then I can be 95% confident that the population mean mu is within 2 standard deviations of x bar. So here I have my x bar. I don't know what the population mean is, but I can be 95% confident that mu is within 2 standard errors of x bar. Because, why? Because this says if I have a mu, there's a 95% probability x bar is going to be within 2 standard errors. So I just flip that around, and if I say if I see x bar, I can be 95% confident that mu is within 2 standard errors. This way, right? It's just kind of it's just kind of the reverse logic, right? So when I teach intro stats, I like to say, you know, if there's you always see a man walking his dog, okay? And so if you see the man walking his dog, if you see the man, you can be the dog's going to be nearby, okay? And then if one day, if you see the dog, you can be confident that the man is nearby, right? So it's just kind of this, the dog always follows the man around, but so wherever you see the man, you know the dog's nearby, but you can flip it around, and one day if you see the dog first, you can also be confident that the man is nearby, okay? And so that forms the foundation for a confidence interval. There is an issue, is that when you do the confidence interval, what? Sigma over the square root of n, this is unknown because we don't know the population standard deviation sigma. So what do? We say, well, I'm going to take my best guess for what the standard deviation is. The best guess I have available to me is my sample standard deviation S. Okay, reasonable thing to say my best guess for the population standard deviation is my sample standard deviation. That's reasonable. But that does introduce extra uncertainty. So the way we fix that or compensate for that is we, instead of using your normal distribution in 1.96, you use the t distribution, and you inflate that number. Instead of 1.96, you use something from the t distribution. It becomes what, 2.1, 2.2, whatever, how many degrees of freedom you have. And the smaller your sample size, the bigger your t becomes to kind of compensate for the additional uncertainty. Right? And so there's our confidence interval. When we create our confidence interval, we have to say I'm 95% confident that the population mean mu is within 2 standard deviations. Why don't we ever say that there's a 95% probability the population mean is within 2 standard deviations of x bar? Right? We learned this in our intro stats class. You have to say I'm 95% confident, and we're not allowed to say 95% probability. You guys remember why though? Oh, well, I'll tell you then. At least for frequentist statistics, okay? And this is different for Bayesian stats, so like in the future you might do some Bayesian stats. For frequentist statistics, probability only exists for things that are uncertain. So if I have a coin, before I flip the coin, I can say, what is the probability that the coin will land heads? And you'd say there's a 50% probability that the coin will land heads, and that's right. Okay, so you flip the coin, and it lands. Okay. Once the coin lands, the question, what is the probability that the coin has landed heads, is a nonsense question. Okay, there's no probability anymore because the coin either landed heads or it didn't land heads. So to ask the question, what is the probability that it landed heads, that it has landed heads, is nonsense because there's no probability. It's a fact of either it did or it didn't land heads. Now you don't know how it landed, so you have to say, I'm 50% confident that it landed heads, okay? But you cannot say there's a 50% probability that it has landed heads because, again, it either did or it didn't land heads. And so when we're talking about, like, is the population mean mu, this is unknown to us, this value mu, is that inside the bounds of my confidence interval? We don't know if it is or if it isn't, okay? But this value mu is some exact value. If we could freeze time, we could measure every single person in the population, and there would be one exact value for what mu is. We don't know what that exact value for mu is, so we can't say yes or no, but we can say, I'm confident, I'm 95% confident that it's within, the upper and lower bounds of my interval. But it's not correct to say there's a 95% probability because there's no uncertainty about mu. It's either in this interval or it's not, okay? At least that's how it works for frequentist statistics. In Bayesian stats, we say, oh, you know what, mu itself is a random variable, and there's a 95% probability that it's inside the interval, and that's okay. So the analog. So certain things, frequentist statistics make more sense, like flipping the coin. Did it land heads or tails? I think a frequentist approach for that makes sense because either it did or it didn't land heads. But then something like, what is the mean age of people in the United States? What is the mean age of people in the United States? Frequentist statistics would require us to have this idea of, like, I have to freeze time at this very instant, and I have to measure exactly every single person's age, and I need to know how old everybody is. Because the reality is every second that ticks by, we're getting older, okay? And our mean age is changing ever so slightly, okay? And also every second or every minute somebody is born, and that's going to affect what the mean age. Every minute somebody dies, that affects what the mean age is. And so what is the mean age of people in the United States? Bayesian stats would say, you know what, it's subject to kind of these random forces, and so we should treat the mean age of the population as a random variable that's subject to kind of randomness, right? Because every second it's changing, every moment, you know, people born, people dying, people enter the U.S., people leave the U.S., and so however you define your thing, there's random forces, so it's better to treat it as a random variable. Frequentist statistics would say, like, you gotta, like, freeze time, you know, like, I don't know if this is a thing that they still do in movies or TV shows where it's like freeze frame, and then, like, they talk to the camera or something. You might be wondering how I got into this situation. Okay. So anyway, that's kind of the difference there. Let me give you your second view quiz answer. The letter C, C as in cat. C as in cat. Okay. So that was the confidence interval. We also have hypothesis testing. We can approach statistical inference from another approach, and that is hypothesis testing, where we have a hypothesis, a null hypothesis, and we test it against our data to see if it holds up, right? So we test the hypothesis against our data, so it's hypothesis testing. And why do we call it a hypothesis? Well, because we say if the null hypothesis were true, what would the world look like? What would the sampling distributions look like? So we imagine this hypothetical situation, this hypothetical population with a hypothetical mean and standard deviation. And based on these hypothetical things, we perform calculations to see, like, how likely could this imaginary hypothetical population produce this random sample that I actually have. Okay? And so, you know, one of the most basic hypothesis tests that you should be familiar with is like the two independent sample t-test, where we have two samples, and sample 1 comes from population 1, sample 2 comes from population 2, and we want to know, do population 1 and population 2, do they have the same mean? Or do we have evidence that population 1 and population 2 have different means? And the null hypothesis here would be that there's no difference between the mean of population 1 and the mean of population 2, that they are the same. And if that were true, if the null hypothesis there were true, any difference that we observe between sample 1's mean and sample 2's mean is just because of kind of the random sampling process. We go and we do calculations. We figure out a p-value. P-value is the probability of getting our data or something more extreme, more unusual, if the null hypothesis were true. And we say, you know what, if the null hypothesis were true, we have these two imaginary hypothetical populations that do have the same mean, and if that were the case, when I take a random sample from this population and a random sample from this population, my two random samples should look pretty similar to each other, okay? And when I calculate, and what I specifically mean by that is that the mean of sample 1 and the mean of sample 2 should be pretty close to each other, right? If that hypothesis were true. So we would expect the difference between these two sample means to be 0. And if they're not equal, if the difference isn't equal to 0, what is that difference significantly different from 0 is what we want to know. We're going to do our calculations of the p-value. If the two populations had means that were equal, what's the probability that from random sampling alone we would get two random samples where the difference is whatever we observed or something bigger? When you do this, your null hypothesis is basically mu1 and mu2, mean of population 1 and the mean of population 2 are equal to each other. Your null hypothesis, this is a point that I very strongly try to make in my intro stats classes, that the null hypothesis always has an equal sign. Okay, you're not going to have a greater than sign or a less than sign in the null hypothesis, and that's because we have to be able to imagine what our world looks like if the null hypothesis were true. And if you just had this thing like mu1 is greater than mu2, then you have like infinitely many possible things for what the world could look like, right? You could have one where mu1 is 10 points bigger than mu2. You could imagine a world where mu1 is 100 points bigger than mu2, or you can imagine a world where mu1 is 1,000 points bigger than mu2. And you have infinitely many possibilities for how you could imagine the world to be if you just said mu1 is greater than mu2. But if you say mu1 is equal to mu2, then the world can only look one particular way. And we need to be able to imagine what this world looks like if the null hypothesis were true. So anyway, we go out and we collect data, and we get x bar 1 is 10, x bar 2 is 12.5. And I wrote, is the observed difference, and it should say of 2.5 significant. I forgot, left that off there. Is that difference between 10 and 12.5, that difference of 2.5 points, is that statistically significant? Answer is always, it depends. Depends on the data and things like that. Okay, let me give you your second answer, which is the letter C. Oh, third answer? I need to give you your third answer? All right. Okay.
We got the C already.
I already gave you the C. Okay, my bad. Okay, third answer is B. B as in bear. Okay, third answer is B. So, is this difference of 2.5 significant? If the standard error of your data is small, this difference of 2.5 will be significant, okay? So if, let's say sample 1 is 10, 10.1, 9.9, 9.8, 10.2, or something like that. And all of the values are centered around 10, but there's very little spread around 10. And then sample 2, your values are 12, 12.5, 12.6, 12.4, and they're centered around 12.5, but they're very kind of close there. You have very small standard errors. You'd say that difference of 2.5 is huge, okay? But if your samples were all, for sample 1, were all over the place, you got 0, 20, 5, 15, okay? Centered around 10, but lots of spread. Sample 2 also, they're all over the place. You get 0, 20, 25, something like that. Centered around 12, the mean ends up being 12, but they're also all over the place. You'd say, you know what, maybe this difference of 2.5, not that big of a deal, okay? And so you say, well, if the probability of getting our data, if the null hypothesis were true, is something small, okay, it means random chance is unlikely to produce these values. And so, therefore, the fact that we actually do have these values indicates to us that our null hypothesis is wrong, right? We did get, so if you say, if the null hypothesis were true, it should be almost impossible to get my data here, okay? But I did get this data. So how could that be? Well, the only way that it could be is either the null hypothesis is true and this really remarkable circumstance happened, this strange set of coincidences happened to produce this so-called nearly impossible data, or perhaps the easier explanation is the null hypothesis isn't true and therefore I'm getting this data, okay? And so if the p-value ends up being small, you say, well, I don't think the null hypothesis is true. You reject the null hypothesis. Because, technically the null hypothesis could be true and just these weird set of circumstances led to this particular data, right? It's kind of like just this very unfortunate series of circumstances puts you at the wrong place at the wrong time, and, it looks like you did something that you didn't do. Like, that could happen, okay? But usually the easier explanation is, this null hypothesis isn't true, and that's how we're getting our data, okay? So p-value is small as you reject the null hypothesis. If the p-value is large, on the other hand, it says, the data that you have isn't that unusual, and even if it doesn't align exactly with the null hypothesis, it's very possible that our data is produced by randomness. And so in that case, you'd say, I don't have enough evidence to reject the null hypothesis, and you do not reject the null. Again, when I teach the class, I very strongly try to impress upon my students to only use the phrases reject the null hypothesis or do not reject the null hypothesis We never use the phrase we accept the null hypothesis. That's a big no-no, okay? So either we reject the null or we do not reject the null, okay? All of these tests that use the central limit theorem, this is what we call parametric tests. They rely on kind of this mathematical theory and stuff, and you prove a lot of these things in like 100B and whatnot. What we're going to do is we're going to kind of do computational-based tests in the next couple weeks, and so we'll look at things like randomization tests and bootstrap tests, and those things don't rely on these parametric central limit theorem things. We just kind of rely on this concept of maybe exchangeability, or this concept of this randomization that we're able to generate, okay? And so that's what we're going to be doing next week. I'm going to run out of time to go over these last few slides, so please just kind of read over them on your own time. But this covers data collection. And the two kind of key ideas here in data collection are that we can have random samples and we can have random assignment. And so this is just some silly scenario where we're trying to do some study on vitamin C and canker sores and things like that. And I go through these 4 scenarios. Some have random sampling, some have random assignment. So this first one has neither random sampling nor random assignment. And what kind of conclusions can we draw? This one has no random sampling, but yes, random assignment. This one has random sampling, but no random assignment. And this last one has both random sampling and random assignment. And I go through kind of like what kind of conclusions can be drawn. The summary is basically, if you have random sampling, you can then generalize your conclusions to the general population, because your random samples should be representative of the general population. The other thing is, if you have random assignment, you can draw a cause and effect conclusion with random assignment. So if you do an experiment where there is random assignment, you can say, I'm observing some kind of difference between these two groups at the end of the study, and because everything else was, when we randomize things, the treatment group and the control group should look fairly similar at the beginning, and the only real difference that we can appreciate between the treatment and the control is that the treatment was randomly assigned treatment, control was assigned control, and therefore any difference we observe between the two groups is because this one was treatment and this one was control. So you can draw cause and effect conclusions. So random assignment, you can draw cause and effect conclusions. Random sampling, you can then generalize to the population. This last situation where we have both random sampling and random assignment is kind of a fantasy situation that almost never happens in real life, okay? Because anytime you do an experiment with random assignment, you have to get consent from the people participating in your study. And as soon as somebody says, no, I don't want to participate in your study, it's no longer a random sample, okay? So you might have like randomly selected people and you say, hey, do you want to participate in my study? And as soon as somebody says, no, I don't want to participate in the study, it's no longer a random sample. So the idea of having both a random sample and random assignment just doesn't really exist in real life. It's fun to kind of imagine and fantasize about, but it's not really gonna happen. So in general, you either have a random experiment with random assignment, but you don't have a random sample. And if you want to generalize your thing, you're hoping to replicate the results of your study with another different group where you do random. So maybe you do a study in the US and you do random assignment and you get these results. And then you go to another country like China and you do the same kind of study. And if you get the same results there and then you go to Europe or another nation and you're kind of getting consistent results everywhere you go where you're doing the same random experiment, then you can say, oh, okay, yeah, this is something that holds true. But if you're not doing that, or maybe if you're just doing within the US, you might want to do like different populations within the US or something like that. But otherwise, it's tough to do. So anyway, that's what we have. So yeah, just review these slides on your own time. Okay, we will wrap things up here. Have a great weekend. We'll see you Monday. Ready for week 9.